The digital twin has arrived. A virtual representation of a connected physical asset made possible by combining advanced simulation and analytics. Right now, digital twins can predict the future, providing preventive maintenance, optimizing performance, and avoiding product failures. ANSYS Twin Builder makes all this a reality by connecting the power of simulation with real-world operations. Twin Builder offers a complete approach to build, validate, and deploy simulation-based digital twins in the cloud or on edge. First comes build. Twin Builder combines the speed of system-level simulation with the accuracy of 3D physics solvers and allows the reuse of existing components through reduced order modeling. ANSYS Twin Builder quickly embeds performance information, cutting runtimes from weeks to hours. Second is to validate. Combining multi-domain systems simulation capabilities with systems validation and optimization. Third, it's time to deploy. Twin Builder creates simpler, highly sophisticated models for real-time deployment. Combining ANSYS simulation and your in-house data yields highly accurate and useful results. The proof and promise of this technology is remarkable. Twin Builder's success in predicting turbine stresses saved a utility more than $100,000 a year in avoiding unplanned outages. Twin Builder accurately analyzed the thermal behavior of a manufacturer's motors within milliseconds, not days. Twin Builder speeds the shift to zero carbon by controlling industrial processes, anticipating carbon reduction options, and lowering maintenance costs. The digital twin has arrived in a big way, connecting rapid, reliable system simulations and real-time, real-life operations. Build, validate, and deploy simulation-based digital twins with ANSYS Twin Builder.
Okay, good afternoon everyone. My name is Vicky Suresh Kaur from ARK Infosolutions, and I work as an application engineer in the segments of electric vehicle and the digital twin technology. So I have been working here at ARK Infosolutions as a application engineer, and now I will go through with the digital twin technology how you can use the ANSYS Twin Builder, which is our software for the digital twin technology. You can incorporate in your applications and try to use the ANSYS Twin Builder. So now let's get started. First I will go through with the product portfolio of ANSYS in simulation industry. What are the products that ANSYS offers, and then we will start our main discussion on the digital twin technology. So this is our ANSYS product portfolio, which offers the software on the simulation industry, on every industry. It is not like about the only specific industry. It is in industries like autonomous vehicles, electric vehicles, electronics, semiconductor, structures, fluids, optics. Also in the machine engineering, the STK software is there. Also it has the cloud-based software also, and it supports the system coupling as well as the HPC, high performance computing, to reduce the simulation time and to get the results faster and then it has also for the like cyber security analysis the made in it tools is there, and then the for the embedded software like for the code generation purpose the scaled one is there also. So this is basically the broad portfolio of ANSYS. It offers it around all the industries, in materials, in electronics, semiconductor structures, in all industries, and our main focus is on the digital twin technology here. Digital twin, it has two software: twin builder, ANSYS twin builder, and ANSYS twin AI. So for the digital twin technology we use both the software to predict the future of any product, like on the basis of past data we predict the future of that product. Now this is our agenda for the today's sessions. First we go through with the digital twin technology, how the digital twin technology works and what is actually the digital twin technology. Then it has some components, we will go through with that components, which are the components that are included in digital twin technology. And then it uses the physics based simulations to enhancing the digital twins. It uses the physics based simulation, so it may be structure physics, your electronics, your semiconductor, your fluid physics. These are the multi physics applications are there, and it uses that physics based simulation to predict the future, predict the outcomes of that product on the basis of their past and the present data. Then how ANSYS twin builder powers the digital twin development, that also we can see. And then we will go through with some industrial applications and real world use cases where this has been actually used and currently uses. The companies like ABB is there, the Rockwell Automation. So these are the multinational companies are there. They are using the ANSYS twin builder for their digital twin technology and predict the, like for the predictive maintenance. They first gather the data and according to that data they predict the failure, when the products might be get failure in future. Now the first thing is, what is the simulation based digital twin? So itself in the name you can see digital twin. So twin means it is like the replica, the clone model you can say, right? So in digital twins we basically make the digital replica of the physical asset. So whatever the physical asset that we have, we just make the replica of that physical asset and track the behavior. By using the physical sensor we track the behavior of the physical asset, and according to that behavior, according to that past and present data we predict the future. Means in future, after suppose 1 year, how this product behaves, what are the capabilities and what are the capabilities might be disturbed for this product, to predict the efficiency, how efficient that product would be in like in next 5 years, how efficient that product would be. So that simulations basically we did in the digital twin technology. Here you can say itself like the sensor has been mounted on the physical asset. So according to that sensor we gather the present data and we also has the past data. So according to the present and past and present data we predict the future. Means in future after 5 years how this product will behave. Next, in digital twin technology, the many industries are there. The industries like aerospace is there, automotive, manufacturing, building and infrastructure, oil and gas. Like in aerospace applications, for example, one airline is there. They use the ANSYS twin builder or the digital twin technology, or they incorporated the digital twin technology in their engine system. Okay, the aerospace engine system. So what is the output from that engine system? They incorporate that digital twins is they find out the maintenance times, when we have to maintain or when we have to do the maintenance of that aerospace engine. So that basically that in aerospace engines did. Then the two major giants like they are basically focused on the manufacturing of aerospace engines, which is GE, and the GE Aerospace is there, and the Rolls Royce. They basically manufacture the aerospace engine, and they currently they are using this digital twin technology, and they predict their maintenance times, when the engine is to get maintained, and actually what is the failure time, so that they track the behavior of that aerospace engine to reduce the cost as well as the failure probability. Then in automotive sector, the many automotive sectors are there, like in manufacturing, the many automotive giants are using the digital twin technology to give the owners, to the car owners, like freedom, or you can say the smarter and smarter solutions for the automotive. Like suppose if safe driving car is there, many times what happens in electric vehicles, the battery might be fired, the might be get catch fired. So that basically the applications are there in automotive segments, they are also using. And in manufacturing, to process and automate the manufacturing industry, means automate the product line of the manufacturing. So for that the digital twin is very helpful, and like for the building and infrastructure. And then in the oil and gas industry also, they are also useful in the oil and gas industry, as the first applications of digital twin is find on the that oil and gas applications. The first use of digital twin is used in the oil and gas application. Like here they find out the temperature data, like they, here in the image itself you can say this is the physical asset, and here is the digital replica of that physical asset, and they find out the temperature at each point, what is the temperature of each point, by using the virtual sensor. So in many applications, like the ship application is also there, where you cannot incorporate or place the sensor at particular place. In physically it is not possible, but in virtually it is possible. In virtual model you can place the sensor anywhere you want, and you can gather the data, like temperature data, like all other data, whatever the data that you want, you can gather this data by using the real life sensors. Then these are the asset qualification of the digital twins. Here in all industries they are using, like high value, energy intensive, mission critical, and deployable in fleet. These are the four economic impact is there. Now we are basically talking about the key elements of digital twin. So the what are the key elements of digital twin? Is that first simulation based and hybrid analytics, then database analytics, because it gathered the data and analyze those data. It is not directly gathered the data and give you. It is first gathered the data by using the physical sensor, and then that data is to be get analyzed after that on the IoT platforms by using the AI or machine learning models. The predict the future prediction is to be there, and then like here for that IoT platform to deploy the data on the IoT platforms, the digital twin partners with the like SAP is there, PTC, Microsoft, Rockwell Automations. So these are the partners of ANSYS digital twin for their deployment data on the IoT platform. So these are basically the partners for the IoT. Now how this actually the workflow is there. First create the virtual sensor to measure the missing data. First we have to create the sensors and place the sensor like anywhere, like in motor at the particular pole we have to measure the temperature data. Okay, so that particular place we have to create one virtual sensor, and we have to rename that sensor, like this is my sensor 1, and by using that sensor 1 I am getting this data. and then perform what ifs before applying the solution. Means after the sensor apply, we have to solve that model and then we analyze the data. Means whatever the data we get by using that sensor, we analyze those data with the by using based on their physical principle, and then we have to analyze the data and see what is the outcomes on this data. So that particularly it is not possible in physically, so that things we do in the virtual environment. Now here the workflow of any physical asset that you can see. This is our first physical asset, and we incorporate the sensors on this motor models. Okay, the sensor get the data or give the data to the IoT based platform. Then here we have a same digital twin model or twin builder model, you can say the virtual model. It is not the actual physical model, it is a virtual model. We build the twin model, then we deploy the data on the connect with that digital twin model with the IoT platform, and on the basis of that sensor data. Now this is our you can say the online digital twin, and this is our offline digital twin. Okay, that means offline data. So that data through sensor, you can say the data is gathered by this model, perform the operations, and then give the insight to the model here, and you can see this information in the dashboard. So it is like the workflow is there. So basically that twin builder model gives you the insights, like what it becomes after 10 years, after 15 years, what is the future capability of that models, when it needs to be maintained. So that's informations that give you by the twin builder model. And now this is the one proposition for the electric drive applications, where we basically use twin builder for the system configuration or the system simulations and the troubleshooting purposes. Next, for the predictive and prescriptive maintenance also there. The predictive maintenance is like to maintain that model. Like first we have to collect the data collections, then you have to analyze those data, then you have to connect that data with the ML machine learning or AI model to predict the future performance, and then we see, and according to the data we see how we can analyze or optimize the data. Now we will go you through with the technical solution architecture of the ANSYS twin builder. The first one, the ANSYS twin builder basically has the four main capabilities are there. So the first one being multi-technology platforms. The multi-technology platform means it has supported like the coupled or co-simulations or the physics-based simulation models. So it has like the different libraries are there. You can see here the different libraries are there. Multi-domain system model, the different libraries are there, like Modelica libraries are there, C++, VHDL AMS. These are the multi-technology libraries are there. Now the second point is state-of-art reduced order modeling or the ROM models. Okay, the ROM techniques it is basically used. Then the third one is interoperability support. The interoperability support means it is like the open platform. So if you want to import the data on the ANSYS twin builder, or you have to import this ANSYS twin builder data into the other platform, like you have a MATLAB data and now you want to import that MATLAB data into the ANSYS twin builder, so that capability is also there. So means it is supported by the third party models also. Okay, then the fourth one is ability to deploy simulation models as runtime for the digital twin. Means it has an edge, or an you can say the IoT platforms are there. Okay, so ability to deploy the runtimes for the digital twins. I also mentioned like SAP, Rockwell Automation, Microsoft, PTC. These are the partners for the IoT platform to deploy the actual digital twin model, or you can say the digital twin builder model. This is the digital twin solution architecture. Here you can build the full system level simulation models by using the 0D models. So 0D models is basically like uh, it has not spatial dimensions. Whatever the spatial dimension you have, like your length, width, height, these are or volume, area. So these are the spatial dimension you have, right? So they are not considered in the digital twins. It is considered like the lump model. Okay, so it is based on the times, whatever the data that you have, it solves on the based on the time, and the function is like here we have to create the ROM model. ROM model is basically it is the compressed models with the accuracy is there also, accuracy and the dominant data, whatever the dominant data that you have in your model, that compress that dominant data means and retrain the that dominant data, and by using those dominant data it solves for the model. And basically it uses the raw model is used to reduce the simulation time. And here after here also the third party software data is also there. FMI unit or FME unit is there, functional mock-up interface or unit you can say, and the existing libraries are there in ANSYS Twin Builder. I already told like VHDL, AMS, Spice, Modelica, C, C++. These are the existing libraries are there. By using that existing library, you can make first the ROM model, and then you can deploy this ROM model into the platforms like here the Rockwell Automation, SAP. These are the partners for the digital twin deployment. Or you can deploy your ANSYS Twin Builder model into the another simulation software. So for that what you have to do, you have to convert your digital twin model as a functional mock-up unit, and this FMU unit you can transfer it to the another third-party software or the another simulation software which supports the digital twin capability. Like I have already said, it is like the physics based simulation, right? So in physics based simulations basically we are mainly focus on the three physics. So which are the three physics are there? The thermal means your fluid, electronics and the structure physics. It has the ANSYS Twin Builder has the library for the fluid power library also there, heat and cooling library, EV powertrain library, structural library. So all the libraries are there inside the ANSYS Twin Builder. You have to use those libraries and create your system level model. Like here it composes hydraulic, thermal, mechanical, all the domain libraries are there. You have to just drag and drop these libraries or the components from the libraries, and you have to make your model, your system level model, and you can simulate this model by using the ANSYS Twin Builder. Then this is one basic model or the key application of electrification libraries that you can say. Now the 3D reduced order modeling interface. The reduced order modeling means this is basically the ROM model. So it is the compressed model of your 3D physics model. So it maintain your dominant data, whatever the dominant data that you have in your 3D physics, and it solves that data in the 0D applications as an 0D application or your lump model. So by using that lump model, it reduces the time of your simulations. Here you can see in the real time you can see the results here. And for this fluent, like the high fidelity fluent model is there for the thermal applications, it uses around 3 hours on the 12 cores. By using 12 cores and 3 hours, and here the real time you can see the results also. Now you can see the difference here. Okay, there is no difference in the results, but very much high difference in your simulation times. It is the actual time, and it requires around the 3 hours to simulate this behavior. Okay, means by using the raw model you can increase your simulation time by 10 to 100x. Then the ROM means the reduced order model has the two types of, like you have the static ROM or the transient ROM or dynamic ROM you can say. And then in these the two categories are the linear and non-linear. The linear means like your conduction, your convection. Okay, in conduction application or convection applications, what it is, the heat flux, whatever the heat flux is there, so that heat is directly proportional to the temperature. Means your temperature, whatever the temperature you have, it is directly proportional to that heat flux gradient. Okay, that heat flux you can say. Okay, so it is the linear behavior. If the temperature is increased, your heat flux or that gradient is also getting increased. But you can say, like in the radiation application, suppose that in radiation applications, whatever the radiation factor is there, it is directly proportional to the T to the power 4. Means it is a non-linear behavior. So if you one times increase that radiation factor, that temperature value you have to increase by 4 factor, means your T to the power 4. So it is the non-linear behavior. So on that basis it has two types, like linear and non-linear, and it is same for the mechanical as well as this electrical applications also. Like in mechanical, your stress is directly proportional to your force, right? So if you increase the force value, the stress value is also getting increased if you keep the area constant. And suppose the same material is there, the linear material is there, and if we have the non-linear material, this function, the stress is not directly proportional to us, because the non-linear materials are there. If you include the non-linear materials, so it comes under the non-linear ROM type, and if the properties are linear, then it comes in the linear ROM. Then how the ROM workflow works here? First we have to create the ROM 2D or 3D solvers and twin builder. By using, we have to create the ROM. And now you can see for the parameter sweep, it takes the time, it is around seconds. First to train the data, training data generations, it takes around hours and days. Then for extraction ROM model, it takes around minutes. And now to solve that model, ROM consumption means to solve that model, it takes seconds. Means within the seconds you can solve the model. Okay, means you can get the data by using, within seconds you can get the real-time data. Now we will see some application examples. Okay, so in which applications you can use this digital twins. So multiple applications are there. Like this application is based on your, this is the interface of the, basically the ANSYS Maxwell interface that you can see. This one, and this one is also the ANSYS Maxwell interface, which has capability to do the advanced magnetic analysis. Like this one is the skew model. Okay, that skew model in the electric machines we basically use to reduce our fudging effect. Okay, and here is the material data to calculate the materials data. Like the non-linear material, if you have, then you have to give the BH curve data. If you want to calculate the core loss, the different models are there, core losses. Here we have to give the also BH curve data. If you want to calculate the demagnetizations, your coercivity data will be important. So that functions, it has the material libraries there. You can pick your material and do the simulations. Now this is the one system model, the power electronics model that we build in the ANSYS twin builder environment. That you can see the various circuits are there. These are the ROM models also there, and you can see the results like winding currents, 25 volt output, 5 volt output, winding voltages. These are the power supply models are there. This basically the model of the flyback converter. Then the semiconductor models, turn on. Now you can see the results. Detailed magnetic models also there. Now for the power electronic drive, which are the components are there, like DC supply components there, MOSFET bridge is there, your stepper motor, this is your motor model, the SML you can see. the mechanical elements also there, the hysteresis control also there. Now you can see here all the models are there, means all the physics are included here. Mechanical is also there, your electrical is also there, your raw model is also there, your MOSFET, and your hysteresis control also there, means this is like your feedback values. Okay. So if you want to use in place of hysteresis, you can use the PI control also to get the feedback system. And this is the data you can see by using the do the analysis. After do the analysis, you can see the results like this for the specific parameters. Now here this is one the electromechanical system integration. Electromechanical means it includes electrical as well as the mechanical systems. Like it has the electric machine actuator. This is our mechanical system, rigid body dynamics model. The one robotics model is there, and this is our power electronics component. And the SCADA controller is also there. And we all do the analysis here. At each point, the electric machines is getting it. So electric machines is getting controlled by the controller and the power electronic circuit. And also the rigid body dynamics means the RBD is also in functions with the mechanical part. So that basically the system level integration of the electromechanical system. Now this is the powertrain system integration for the EV models. Here the inverter subsystem is the heart of, you can say, your powertrain system. The inverter is the heart of your powertrain system. So inverter subsystems, this subsystem also has the some subsystems are there, right? So like your battery, these are the different MOSFETs, these are the subsystems are there. Okay, your inverter subsystem, your power electronics inverter, this is one the subsystem of the whole this system integration. The power source is our subsystem, traction motor is the subsystem of the system simulation. Then the embedded control, the SCADA tools are there, the mechanical and dynamic loads are there. So by using all these multi-physics models, you can play an important role in the system simulation of the electric vehicle technology. Means full electric vehicles you can simulate here. Whatever the data that you have for the electric machines, you can place at the one environment and you can see the effect. If you connect all these physics at once, now you can see how the behavior are changes and what are the changes in the behavior. And by using the raw models, you can simulate the data within the lesser time, as you have to simulate the data by using the high fidelity models are there. Like for the mechanical, the workbench is there, mechanical is there, and for the electric machines like MotorCAD, RM Expert, Maxwell is there. So these are the high fidelity models, but you have to convert these high fidelity models into the raw model, and by using the raw models you can simulate the data within the second. Within second you can see the results for the system simulation. Now this is one the architecture of the battery management system, which is integration with the ECM and the thermal models. So here this is the thermal models, the temperature of battery, and this is the liquid cooling library of Modelica liquid cooling library. So Modelica library is also included in the twin builder environment. You have to just use that library. And here this boost converter is also made up by using these libraries, the electrical libraries here there. This is the liquid cooling library and this is the raw model for the battery. And now you can see the results, like cell temperature is there with according to the time. As the time passes, how the temperature is going to be changed there. After cooling, what is the change, target voltage mode. So these are the different results that you can see by using the ANSYS twin builder. Now we will see some case studies are there. Okay, so case studies, like this is the one case study of the phonics contact. Okay, so basically they are manufactured or working in the relay application. Okay, So like they want to predict the failure of the relay, because they has to spend around tens of thousands of dollars per hour, because their relay is getting failed, and for that failure they have to pay 10 means 10k dollars per hour. Okay, so by using ANSYS twin builder, what they can do, because in actual what happens, there is no wear sensor is there, you cannot measure the wear, okay, by using the physical sensor. So that wear is to be measured by using the virtual sensors. First they make their virtual model by using the digital twins, they make the virtual model of their systems, and they place the wear sensor at this particular virtual model in the virtual model, and they gather the data about the wear, what is the value there, and what are the data about like actual load and sensor data, temperature is there, switching frequency value is there. Okay, so they gather the data. After gather the data, they potentially find out the cause and they fix that cause. So as of now, by using the ANSYS twin builder, they save their tens of $1,000 per hours, because every time they use the relay get fed, and they have to reconstruct that relay, they have to pay like $10,000. Now the other one case study is like Volkswagen is there. You all know heard about the VW group. Okay, so that Volkswagen is also uses the multi-physics simulation, the ROM models of the ANSYS twin builder for their battery pack optimization. Means they want to participate in the race. So for that the electric vehicle race is there. So for that they want to optimize their battery pack. So they use the ANSYS ROM models here. Thermal ROM models are there. Thermal ROM model, and by using the digital twin technology and the ANSYS twin builder, they optimize their battery pack and also won the race by full 15 seconds on the 24th June with the help of their by using their ANSYS technology. This is the one application of the electric pump, you can say. These are the ROM models. This is the thermal model. Sorry, this is your electric machine model. This is electric machine model. This is the mechanical model. This one is the input and output pressure, means this simulation is done in the fluent. Your fluid capabilities. Then it is your structural, reservoir, variable wall sections are there. All the things are included here. The like walls, when the flow is there, what is the flow rate. To measure that flow rate, the flow meter is also added there, and after that they gather the data and see how the multiphysics ROM helps to get the data about how the electric pump is getting used, at which times they have to off the pump or on the pump, what is the electric current that might require to run the motor. So that whole system level model simulations they can do by using the twin builder. This is the one electric motor model. You can see the system integration in ANSYS twin builder, thermal ROM, and these are the circuit level simulations. And after this system level integration, they deploy the digital twin model into the PTC workbench. Here things work. The PTC workbench is there. In the PTC things works. They deploy the digital twin model, and now they can see the results. We have some public customer references on the digital twin technology also. Now you can see how actually this key technologies from concept to production is work in the digital twin concept. Like first you have to make the CAD drawings. After the CAD drawings, you have to make your 3D physics models. 3D physics model means you have to do the physics based simulations, okay, like structure, fluids or electronics. Then after the 3D physics models, you have to make the ROM model. So what is the need of that ROM model is to reduce the time, because when you are you are doing the 3D physics based simulations, they are basically uses the high fidelity models. Okay, the high fidelity solvers, they solve for each and every direction, like 3D is there, and they gather the data, and also they take more time to solve the data. Means the to solve the models they will take more time. Okay, so now what ROM model can do? ROM model is basically uses the 0D solver. Okay, 0D means whatever the dimensions are there, spatial dimension, it is not considered, and they considered only the dominant data, whatever the dominant data you have in your 3D physics models. Okay, so that dominant data, that ROM model take, okay, and solve this data with the time constraint. Okay, so with the time constraint, because they gather the dominant data from the 3D physics models, what happens? The accuracy is not changing. Okay, whatever the accuracy that you have in your high fidelity model, so the same accuracy you can get by using the ROM model. But the what is the difference between these two simulations is that this simulation takes more time. Like if this simulation takes 10 hours, okay, for one simulation, so that by using the ROM models you can get the results within a minute, or within 1 hour you can get the result. So that fast is the ROM model is there. So that's why in system simulations the ROM model is used to get the system or the results faster. Then in the digital twin technology, the from like the two stages are there. One is the development stage, and next is the production stage. So in the production stage the online digital twin is used, and in the development the offline digital twin is used. Okay, so this is the simulation interface is there. You can see the Studio 5000. So it is the the simulation interface of Rockwell Automation. Okay, so that basically this simulation interface owned by the Rockwell. And for the development phase the emulated controller is used, and in the production phase, because in the production phase we use actual physical controller, so that times the physical controller is used, but the simulation interface is same for both the development and production time. Now this is the one, the reference of Bosch. They designed their battery management system for electric vehicles, and they said like their people said like digital twins change the game up for their OEMs. Means like here in the automotive industry, first they use the physics based simulations and the database simulation. They combine those data and see what is the failure rate is there in future, when it is going to fail. So that basically gives they to maintain and change the proportion, or to reduce their maintenance cost. So whatever the maintenance cost they will get, so basically they reduce their maintenance cost by using the this high fidelity and the physics based and the data analytics model. Okay, also the Porsche Motorsport is there. They also uses the multi physics technology for their electric powertrain. For the industrial autonomy, the ANSYS and AWS are there. Because they collaborate, ANSYS and AWS is collaborate for the autonomous feature. Okay, also Wärtsilä, they also uses they are also in the renewable sector. Okay, so they uses their digital twin. By using the digital twins here, they mention also save the team 6 months of development time. They save the development time of 6 months for their battery system. Okay, and reduce the number of physical prototypes by 3. Means if they cost like they reduce their physical prototype cost by the 3 times. Suppose if the one physical test costs their hundreds of dollars, then they are basically save the $300. Okay. The KTM is also there. You also know this is the one bike company is there. They are also using the multi-physics simulation model in their battery development. This is the low carbon power generation technology is there. So they are also using for, they can minimize the emission slash maintenance cost and maximize their power generation. So they are basically doing these things by using the digital twin technology and the ANSYS multi-physics solution. Here the ABB is also using for their fast tracking next gen electric. So they are basically use the ROM models and to do the system level simulation by using the electric ROM models, electric machines ROM models. They are doing like 2D analysis, then the 3D analysis, and they are going for the system level simulations. And then they, by using the ROM models, they solve their, like, they accomplish their task in just few milliseconds compared to many hour simulations or even days. By traditional technologies, it will take around days or many hours to do the first simulation or to complete one simulations. But by using the ROM models, you can give the same results within millisecond. And this is the one Karcher is there. They are basically develop the electrical floor, floor cleaner, and they build their electric cleaner by using the ANSYS Twin Builder, battery pack, and the Modelica libraries. Tata Steel is also using to improve the maintenance cost. Ingi Lab, Kriegen, and ANSYS Accelerate Zero Carbon Energy, they are also using. This is the one electronics battery pack simulation, the means in the segment of electronics cooling. They reduce the cooling, means if they reduce the cooling part, they have to design the better cooling system. If they design the better cooling systems, their heat up capability is less. That means their batteries don't catch fire in the running applications. If the motor is running for the long hours, so that's battery doesn't catch fire in future. And when it catch fire, they also know like when it is going to be fire at which positions. If my parameters goes beyond this level, my battery is getting catch fire. And then HSD mechatronics is also there. They are also using the electromechanical systems. Here you can see this is the system, the, and here this is the environment of ANSYS, where they simulate their model the structural behavior as well as the electrical behavior also. Danfoss drives are there. This is one test trick. The Yuka is build the test trick and do the finite element analysis on the test tricks and see when the failure is going to be there, when the actual failure occurs. On the basis of their previous data, whatever the previous data that they have, they simulate that data by using the predictive analytics. Like first the data collection is there, and then to analyze the data by using the data, they have to deploy their digital twin model and get the predictive maintenance values, like when it is going to be fire, when it's going to be fail, and at which point actually. It is not like whenever the complex system is there, they actually predict the place where the system is at which place the system is going to fail. This is one Hyundai model is there. They uses the ANSYS twin builder for their EV power optimization and to extend their EV range. Here ANSYS EV digital twin, you can see the traction motors. I will show you one video also on that, how to calculate that EV range. Okay. These are the advanced industrial motor drives are there, and they are also doing the system level simulation here. Here Honeywell is also there. Now thank you for your attention. Okay, if you have any questions you can ask. Yeah, you can unmute yourself and you can ask your questions, or you can put your question in the chat box, so I will give you the answer of that questions. Okay, you can ask your questions. If you have any question you can ask. In the meantime I will show you one video of how to calculate the electric vehicle range. Okay. And now you can see this is the drive cycle data as well as the distance traveled. Means by using this they calculate the distance. Like here the 20 kilometer is the 22, and the SOC is also there. You can see the SOC, how the state of charge is there, and the cell temperature. Also they track the cell temperature and the drive cycles, and the torque is also there. The resistance torque is there. Means they gathered all the data hereby using all the models, means the system simulation models, and they also perform the test on the actual scenario. In virtual scenario, we will gather the data as the data gathered by using the physical scenario. Now you can see here, this is basically the GUI of the ANSYS electronic desktop, in which you can see this is the ANSYS twin builder. Here you can see the twin builder is there. This is the ANSYS twin builder model is there, and here it supports like different ROM models. Here models, different libraries are there, specific domain libraries. SML language is there, Spice, VHDL AMS, Python, Modelica, C model. These are the domain libraries are there. The ROM model supported like static ROM, dynamic ROM, that I already told, mechanical ROM, SI wave, your PCB RAM. Here if you have the PCB ROM, then you can import as an SI wave, Fluent, SCAD, MotorCAD, PE Expert. It is coupling with the Maxwell transient, Simulink also there, data connection, twin co-simulation, RM Expert, Maxwell, Q3D. In it has characteristics, and these are the mock-up units. Means if you have to convert your model within the special mock-up unit, then you can directly convert by using this functional mock-up unit tab. Okay. Now here add component options, where you can add all the components up by using these options, or by using these options you can add the components here. Here in this project, this is the one battery cooling project is there. Okay, I have simulated this data, this battery pack, battery cell is there. Okay, in the Fluent. Okay, and gathered the data. Also I simulate the same model by using the ANSYS twin builder here. Here I place, this is my flow source is there. Okay, where I measure the flow rate in meter cube per seconds. I measure the flow rate, and at which temperature my flow rate is, actually what is the value of my flow rate at the particular temperature. So that value we can see here, and I run these simulations for 100 seconds. Okay, now you can see here the results. Now you can see these results. Okay, this red line is basically the flow rate. Okay, and this line, this one, this gray one, you can see this is the temperature data. So my target temperature value is 310. I have to achieve the target temperature value as 310 Kelvin. Okay, so now you can see as the temperature increases, the flow rate is nothing. As my targeted value is 310 Kelvin. As my targeted value is reached, here the temperature goes beyond my targeted value. So as the temperature goes beyond the targeted value, what is the flow rate is there now? The flow rate, it gives the positive flow rate. Positive means it increases suddenly the flow rate. Suddenly the flow rate increases, and you can see as the flow rate increases, the temperature becomes suddenly decrease. Okay, so as the temperature decrease, and also as the temperature decrease, the flow rate is also getting decrease. Here the temperature is getting slightly up to the targeted value, and it is like the static. Then also the flow rate is also getting upper, and then it maintain at the particular. Means to achieve this 310 targeted temperature, we required basically add a marker the exact value at M1 the exact like 0.1195 meter cube per second flow rate I require to maintain the temperature of that 310. You can see the 309 is the 309.99. To achieve this targeted value, I require this much of flow rate value. So this is one basically the application. Here you can see here the components, like these are the mechanical components are there, the flow components are there, the hydraulic components, and here this is the fluent model, the ROM model, which I export like this. Here fluent, here I placed my model. Okay, and these are the electrical appliances. Here the three physics are there. The one fluid is there, mechanical is there, and the electrical is there. Okay. By using this electrical, we create the circuits and then we do the simulations. Now we get the data by this. I have the target temperature and I have to calculate the flow rate. What is the actual flow rate? The same value I get by using the fluent model, but by using fluent model it takes around 3 to 4 hours. Okay, and by using this ANSYS twin builder, the results will get in seconds. Like I required only I think 4 to 5 seconds, okay, to solve this model, and by using the ANSYS fluent it takes around 3 to 4 hours to calculate the same thing, okay, without disturbing the accuracy of the simulation. So now if you have any questions you can ask. Any questions you have you can ask, and also fill the feedback form also. You can get the free certificates.
Sir, your presentation was very nice.
Okay.
Can you highlight a little bit of virtual sensors?
Okay. Virtual.
Virtual sensors you told, na, that they are
Uh,
using in the work.
yeah.
This one.
The libraries are
Yes.
there. That libraries is included there. In the libraries.
Okay.
Okay. In the libraries, like here, I will show you in the software. Okay. Just a second. I will share my
Please,
screen.
please.
And here component libraries. When I enable these component libraries, here you can see the simpler elements are there. The basic elements here, circuit blocks, all the elements are there, right? Then here on the basis of digital elements are there, digital sources, counters, flip-flop, logic gates. Also there are the power system, the tools, the physics. Here the sensor is also that level 1 model building blocks is there, sensor. These are different sensors are there. Okay, the sensing elements are there. You can use any elements here. It is not like only the few elements are like electrical and electronic components are here, mechanical, hydraulic, whatever the component that you have. If you find hard to find the components, then you can just go here and place the name here. Whenever SVMs like for sensor, here the different elements are coming. Okay, so you can pick the elements here and just drag and drop here like this, and connect the circuit. Whatever the circuit you have to just connect this circuit and simulate the model. By using this analyze button you can simulate the model. So it is just as simple as that. You have to just drag and drop the models, apply the conditions to your models, whatever the time delay, minimum and maximum limit, and the sample time is there. So that thing that you have to give, and then you can analyze the model.